When people say we're going to Mars, it sounds like a destination, like picking a city on a map. But what does going to Mars actually mean in hard numbers and hard risk when you strip away the hype and look at the physics? Because it's not a quick flight, it's not a test drive, it's committing human lives to leave Earth for years and hoping every part of a very long chain works. But before we continue, please subscribe to the channel to give your support. Let's continue. First problem, distance. Mars does not sit at one fixed range from Earth. It keeps moving on its own orbit while we move on ours. In a good alignment, when Earth and Mars are on the same side of the Sun, the distance can drop to about 54.6 million kilometers, roughly 33.9 million miles. In a bad alignment, when they're on opposite sides, it can go beyond 400 million kilometers, around 250 million miles. That's the scale you're dealing with, tens to hundreds of millions of kilometers, and the target itself is moving the whole time. To cross that, you don't just point straight at Mars and fire the engines. You fall into a new path around the Sun. Relative to the Sun, the spacecraft is moving at something like 24 kilometers per second, around 54,000 miles per hour. At that speed, you cross the width of India in a couple of minutes, but it still takes 6 to 9 months to reach Mars on the kind of efficient trajectory we actually know how to fly. So when someone says, we'll just go there, baked into that sentence is half a year or more of exposure to vacuum, radiation, and isolation just for the trip out. So you might think, fine, speed it up, push harder, get there in 3 months instead of 9. Why not just build a stronger rocket and accept the higher speed? Here's where the trade becomes brutal. The standard, fuel-efficient way to go from Earth's orbit to Mars's orbit is called a Hohmann transfer. In simple terms, you do one burn to leave Earth and enter a stretched-out path around the Sun, an ellipse that touches Earth's orbit at one end and Mars is at the other. Then you coast, no thrust, until you meet Mars at the other side. That path is minimum energy. It needs the smallest change in speed, so it needs the least propellant. The cost is time, typically around 8 to 9 months of travel. If you say, I want to do this in about 90 days, the required change in speed jumps a lot. And here's the painful part. Rocket performance is not linear. If you ask for a bit more speed, the propellant you need goes up by a lot, because the fuel you add also has mass, and then you need more fuel to move that fuel, and so on. The relationship between speed change and mass is exponential, which means a little faster very quickly becomes unrealistically huge vehicle. So you're stuck between two bad options. Go slow and efficient and your crew spends more time in deep space, absorbing more radiation and giving more time for something to break. Go fast and you need a massive ship and huge launch costs just to push all that extra propellant off Earth. There is no cheap, quick mode that keeps the risks low and the rocket small. The physics simply doesn't allow it. But there's another hidden trap in that simple phrase, going to Mars. Are you talking about a one-way flag-planting stunt or a serious mission where people come back? In any realistic program, going to Mars means round trip. And the moment you say round trip, the architecture explodes in complexity. Outbound, you have to launch off Earth, reach low Earth orbit, then perform a burn to escape Earth's gravity and set up that interplanetary path. Months later, at Mars, you either slow down into orbit around Mars, or you come in directly and ride the thin atmosphere down to the surface. That alone uses multiple major burns, multiple pieces of critical hardware, and multiple points where failure means loss of mission or a loss of crew. Now mirror that in reverse. At some point later, your crew has to get back off Mars. That means an ascent vehicle on the surface, fully fueled, checked out, and ready to go. It has to launch from Mars, reach orbit around Mars, then do another big burn to head back to Earth, cruise for months, then survive high-speed entry into Earth's atmosphere and final landing. Each of those stages needs engines, tanks, guidance, and redundancy. Some of that hardware has to sit on Mars in the cold, in dust, for years, and then work when humans finally depend on it. If the ascent stage does not start, there is no fast rescue option. Going to Mars for real means designing a multi-year chain of events where any broken link can trap or kill the crew. So the next logical question is, how long are these people actually away from Earth? Not the optimistic headline, the real timeline. On a typical efficient mission, you spend about 6 to 9 months flying from Earth to Mars. Once you land, you can't just leave whenever you feel like it. You need a good alignment of Earth and Mars again, so that the return trip does not require ridiculous fuel. Those good alignments come in a cycle of roughly 26 months. That leads to a standard long-stay mission profile. Fly out for 6 to 9 months, then stay on the surface for around 500 days, which is about a year and a half, while you wait for the next favorable launch window. Then fly back for another 6 to 9 months. Add it up and you're looking at roughly 2.5 to 3 years total time away from Earth. That's not a worst case, that's the baseline. Short stay missions where you leave sooner can cut surface time but often shift more time into spaceflight and can demand more energy, so they have their own penalties. The bottom line is, if you sign humans to go to Mars and back, you're committing them to several years off-world. At this point, there's a simple, harsh question. If it takes that long and it's that risky, why Mars at all? Why not focus on closer targets like the Moon? Or maybe consider Venus, which is more similar to Earth in size. Why pick the harder, farther planet? Venus, on paper, looks attractive. The planet is close in size to Earth and the gravity of the surface is also close to 1 g. But the environment is extreme. The surface temperature is about 460 degrees Celsius, around 860 degrees Fahrenheit. And the pressure is like being almost a kilometer, about 3,000 feet, below the ocean on Earth. Normal materials and electronics don't last long there. Landers die in hours. People sometimes talk about floating habitats high in the Venus atmosphere where the conditions are milder, but that is technology we are nowhere near deploying with crews. The Moon is much closer, only about 3 days away, which is a huge safety advantage. But the Moon has almost no atmosphere, so no air to work with, and the gravity is only about 1/6 of Earth's. There's water ice at the poles, which is promising, but large areas near the equator are extremely dry. A lunar day lasts about 14 Earth days, and so does a lunar night. That means 2 weeks of continuous sunlight heating everything, followed by 2 weeks of darkness where the temperature plummets and your solar panels give you nothing. Surviving that night means big batteries or nuclear reactors. Mars sits in an awkward but useful middle ground. Gravity is about 38% of Earth's, stronger than the Moon but weaker than home, which might be enough to reduce some of the worst long-term health effects of microgravity. A Martian day is about 24.6 hours, almost the same as Earth's day, so your body clock and your power systems can run on a familiar cycle. There is an atmosphere, very thin, less than 1% of Earth's sea level pressure, but it exists, and it's rich in carbon dioxide, which can be turned into oxygen and methane with the right machines. There's frozen water in the polar caps and underground deposits, which means local sources for drinking water, oxygen, fuel, and even radiation shielding if you store it around habitats. So when mission designers say Mars is the main target, they're not saying Mars is friendly. They're saying that compared to Venus's crushing heat and the Moon's 2-week nights and extreme dryness, Mars offers the best overall package for long-term human presence. It's still a cold, dry, thin air world, but it gives you just enough gravity, day length, water, and usable air to build a base that can grow instead of just barely survive. If that's what going to Mars really means in distance, time, and destination, the next hard question is, how do you actually aim a ship at a moving planet with limited fuel, when gravity, not your engines, is really in control? Why isn't just build a bigger rocket and point it at Mars enough? Because the thing really in charge of your mission is not your engine, it's gravity, and it plays by rules you can't negotiate with. You're not steering across a map, you're dropping into very specific paths around the sun. An orbit that you don't hit almost perfectly, you either waste absurd amounts of fuel or you miss Mars completely. So first, who's actually driving the spaceship? You or gravity? Once you're off the launch pad, most of the time it's gravity. The rocket only fires in short, precise burns, and the rest of the trip is coasting along a curved line in space, an orbit. To even get that far, you have to fight Earth's gravity just to reach space. The speed you need to completely escape Earth's pull from the surface is about 11.2 kilometers per second, around 25,000 miles per hour. But you don't go straight from zero to escape. First, you aim for low Earth orbit. To sit there circling Earth, you already need about 7.8 kilometers per second, roughly 17,500 miles per hour. At that point, you're in a kind of high-speed highway around the planet, and you've burned a huge amount of fuel just to get there. The Mars mission stack still needs several more kilometers per second on top of that to climb out of Earth's gravity well and reshape its path into one that reaches Mars. Every extra bit of speed you need is extra propellant mass you had to lift in the first place. That's why gravity is the real boss. It sets the speed targets, and those speed targets tell you how big and heavy your ship has to be. So if the speeds are that extreme, why can't you just leave whenever you're ready? Because the orbits of Earth and Mars turn time into a hard constraint. Earth takes about 1 year to go around the Sun. Mars takes about 1.88 years. That means Earth laps Mars roughly every 26 months. Only during certain parts of that cycle are Earth and Mars positioned so that a relatively low energy trajectory connects them. Those are your launch windows. If you launch inside that window, your spacecraft can follow an efficient path and meet Mars without needing ridiculous amounts of fuel. If you launch outside that window, the geometry gets ugly. You either need far more speed to reach Mars at a weird angle, or you end up on a path that doesn't intercept Mars at all with the engine performance you have. So the calendar becomes as important as engine thrust. It's not fly when you want, it's fly inside this narrow few-week window every 26 months, or accept that your mission just got way more expensive or outright impossible with your current hardware. This brings us to the standard solution the textbooks love, the so-called slow train to Mars. Why do mission planners keep coming back to that? The most fuel-efficient path between two circular orbits is a specific kind of ellipse called a Hohmann transfer. You start in Earth's orbit around the Sun. You do a burn that stretches your path into an elongated loop that touches Earth's orbit at one end and Mars's orbit at the other. Then you coast along that loop until you reach the point where Mars will be, and you either enter orbit around Mars or go straight into its atmosphere. This Hohmann trajectory is designed to minimize the total change in speed you need. That means it minimizes the propellant you have to launch from Earth. The price you pay is time. That path typically takes around 8 to 9 months of flight, and every extra week in deep space means more exposure to cosmic radiation, more wear on your systems, more chances for something to fail. In other words, by saving fuel, you're increasing biological and mechanical risk. That's a hard trade, cheaper and slower versus faster and riskier in a different way. So what if you decide the slow train is not acceptable and you want something faster, like 3 to 4 months to Mars? You absolutely can design higher energy trajectories that cut travel time. The problem is what they do to your speed budget. To get there faster, you need to leave Earth going faster and arrive at Mars going faster, which means you need bigger burns at both ends. This spikes your required change in speed. Because of how rockets work, this is not a gentle increase. The relationship between change in speed and mass is exponential. Put simply, if you want a little more speed, you need a lot more propellant. That extra propellant itself has weight, so you need even more fuel to push it, and the vehicle mass grows very quickly. You go from a big but manageable Mars ship to a monster stack that is difficult or impossible to launch with any current or near-term rocket. This is why just go in 90 days sounds simple, but when you do the math, explodes the size and cost of the mission. So you might ask, can't we cheat using the trick we use for outer planets, where we swing by other worlds and steal a bit of their orbital energy, those gravity assists everyone loves to show in animations? The idea is that you dive close to a planet, let its gravity bend your path, and you leave with a different speed and direction without burning as much fuel. For missions to the outer solar system, past Jupiter or Saturn, gravity assists from Venus, Earth, or Jupiter can be mission-saving. For trips from Earth to Mars, though, the value of gravity assists is smaller, and the complexity goes way up. You could try a flyby of Venus or Earth itself to change your path, but now your timing gets even more constrained. Your trajectory gets longer and more convoluted, and the benefits often don't justify the added risk and time, especially for crewed missions where every extra month in space hurts you. In practice, for early human missions from Earth to Mars, it's usually simpler and safer to do straightforward burns and accept the fuel hit instead of designing multi-planet slingshot tours. Then there's the tempting list of advanced ideas people like to throw around: solar sails, electric tethers, fusion drives with constant thrust, giant plasma engines. These concepts might one day give us the ability to accelerate gently but continuously, shaving down travel time without absurd fuel loads. But right now, they're not ready for carrying humans to Mars and back on a tight schedule. Solar sails need huge areas and work best where sunlight is strong and payloads are light. Fusion and other exotic drives are still at the research or science fiction stage for real missions. High-power electric propulsion is improving, but it's mainly suitable for cargo, not a big crewed ship that needs strong pushes at specific times. So for the first serious human missions to Mars, you are stuck in a narrow box. Gravity dictates the speeds. Orbits dictate the launch windows. Efficient trajectories cut fuel but increase exposure. Fast trajectories reduce time but blow up your mass. Gravity assists and exotic tech are either marginal or not flight ready. Within all of that, you have to pick a path that a real rocket can actually fly. And that leads directly to the next hard problem. If orbits and timing are this unforgiving, what kind of engines and propulsion systems can actually deliver the speed you need without turning the ship into a flying fuel tank that no one can afford to launch? Because you don't just need a rocket, you need the right kind of rocket with the right trade between power, efficiency, and risk. Start with the technology we actually have in our hands right now: chemical rockets. These are the engines you're used to seeing, burning fuel with an oxidizer, throwing hot gas out the back at high speed. Their performance is usually described by something called specific impulse. In plain language, that's how many seconds an engine can produce 1 unit of thrust from 1 unit of propellant. Higher specific impulse means your propellant gives you more push for the same mass. For serious Mars-class vehicles, the main options are liquid oxygen with methane or liquid oxygen with hydrogen. Those combinations can give you something like 350 to 450 seconds of specific impulse in vacuum. That's the zone our best chemical engines live in right now. With that performance and with very large boosters, we can already put more than 100 tons into low Earth orbit in a single launch. But here's the catch. That huge launch stack, which might weigh more than a fully loaded wide-body airliner, is mostly just there to get a relatively small payload to orbit. By the time you've burned through all the booster stages and dropped the empty tanks, what's left is a much smaller spacecraft or upper stage, plus some fuel that can then push towards Mars. So chemical rockets are powerful enough to start building Mars missions, but they are very wasteful in terms of total mass. Most of what you launch is propellant and structure that you throw away on the way up. So you immediately ask, is there a way to get more mileage for each kilogram of propellant so you don't have to build monsters just to send a few people and habitat? That leads to nuclear thermal rockets. Nuclear thermal propulsion keeps the basic idea of a rocket: push mass out the back, but changes how you heat it. Instead of burning chemical fuel with oxygen, you run liquid hydrogen through a compact nuclear reactor. The reactor heats the hydrogen to extremely high temperatures, and that hot hydrogen expands out through a nozzle at very high speed. Because the exhaust is moving faster, the engine-specific impulse can jump to the 800 to 900 second range, roughly double the efficiency of a top-tier chemical engine. What does that extra efficiency actually buy you? You can use it in two main ways. You can keep the ship's size roughly the same and get more total change in speed out of it, which can cut travel time significantly. Or you can keep your mission speed requirements the same and send a larger payload for the same total launch mass. In both cases, nuclear thermal engines could shrink the number of launches you need, reduce how much fuel you have to loft from Earth, or shorten how long your crew is exposed to radiation in deep space. But now you've traded one problem for another. You are firing a nuclear reactor in space, and more importantly, you are launching that reactor from Earth. That raises safety concerns during launch and ascent, engineering questions about keeping the reactor safe on the pad and during abort scenarios, and resistance from anyone who hears nuclear and rocket in the same sentence. From a physics standpoint, nuclear thermal looks very attractive. From a regulatory and public acceptance standpoint, it's a minefield. It will almost certainly fly first without people, probably in cislunar space, before anyone trusts it for crewed missions to Mars. So if chemical rockets are powerful but inefficient, and nuclear thermal is powerful and more efficient, what about systems that aim purely for efficiency, even if they don't push very hard? That's where electric propulsion comes in. Electric thrusters, like ion engines and Hall effect thrusters, don't dump big chunks of hot gas all at once. Instead, they take a propellant like xenon, ionize it, and use electric fields or magnetic fields to accelerate it to extremely high speeds. The exhaust speeds here can reach 20 to 50 kilometers per second, much faster than the exhaust from chemical rockets. That translates to specific impulses in the 1,000 to 3,000 second range, sometimes even a bit higher. In plain terms, for the same mass of propellant, you can get many times more total change in speed than with chemicals. The downside is thrust. These engines produce very tiny forces. Think in terms of the weight of a sheet of paper resting on your hand spread out over a spacecraft that weighs tons. They are not good at lifting off from a planet. They are not good at sudden big burns. What they're good at is firing continuously, very gently, for months or years, slowly building up speed. That makes them ideal for cargo. You can stick a big solar array or reactor on a cargo ship, install electric thrusters, and let it take a year or two to spiral its way from Earth's neighborhood to Mars' orbit. That way, heavy equipment, extra supplies, or propellant can move very efficiently without risking people on ultra-long, low-thrust journeys. For the crew, though, you still need something that can deliver large pushes on demand, for launch, for course corrections, and for capture burns. Electric propulsion alone is not a good fit for a first-generation human transport unless you combine it with other systems in a complex hybrid architecture. And inside all of this talk about engine types, there's a deeper structural trick that makes or breaks a Mars mission: staging and reusability. You almost never have one single rocket that does everything. Instead, you have stages. The lower stages do the dirty work of fighting through the thick atmosphere and most of Earth's gravity. Then they drop away. Upper stages take over in thinner air and vacuum. For Mars missions, you might not even lift the whole Mars stack in one go. You may launch multiple heavy lift rockets, each carrying part of the propellant or part of the hardware. Then you assemble or refuel the ship in low Earth orbit, like building a truck in pieces, then loading the fuel after it's already parked at the top of the hill. That approach spreads the mass over several launches, but adds the complexity of orbital rendezvous, docking, and in-space refueling. Reusability changes the economics again. If your booster can land, be checked out, and launched again many times, your cost per kilogram to orbit drops massively. That is why current launch companies are so obsessed with landing and reusing first stages. But reusability adds its own stress. The hardware has to survive repeated flights through high heating and high acceleration, then still deliver precise performance for a critical Mars mission. It's not enough to be reusable. It has to be reusable and extremely reliable. So when you put it all together, what does a realistic first crewed Mars propulsion system look like? It's probably not some shiny fusion engine or pure ion drive. It's much more likely a stack dominated by high-performance chemical stages, maybe assisted by nuclear thermal or electric propulsion for some segments once those are proven. The boring answer is that the first missions will lean heavily on what we already understand very well, then gradually integrate new tech after it has been tested near Earth or around the Moon. And this leads straight into the next hard truth. No matter which engine you choose, the rocket equation does not back off. The more stuff you try to send, the more fuel you need, and the more fuel you need, the larger and heavier everything becomes. At some point, mass itself becomes your main enemy. Not distance, not speed, just the brutal math of hauling every kilogram off Earth. So here's the next uncomfortable layer. Even if you pick your trajectory perfectly and choose the right engines, there's a simple limit that keeps punching you in the face: mass. The more stuff you try to haul to Mars, the more fuel you need, and the more fuel you add, the heavier the rocket gets, and then you need even more fuel to push that, and it spirals fast. This isn't a vague rockets are heavy problem. It's baked into the core math of how rockets work. In plain language, the relationship between how much you can change your speed and how heavy your rocket is compared to how heavy it is after you burn its fuel is not a straight line. If you say, I want a little more speed, the fuel requirement jumps much more than a little. If you say, I want to carry double the payload, you don't just add double the fuel. The total launch mass can more than double because that fuel itself adds mass, and then you need tanks to hold it, structure to support it, and engines big enough to push it. Every extra kilogram you add at the top, like a bit more food, some extra comfort items, a larger cabin, turns into multiple kilograms of propellant and hardware at the bottom. So you have to be ruthless about what you bring. And that leads straight into the next question. How much stuff do you actually need to keep a small crew alive and functioning for a full Mars mission, around 900 days end to end? Let's do rough numbers in simple terms. Say you fly 4 to 6 people. Each person needs food and water every day, obviously. Before you even talk about recycling, a basic estimate is maybe 1 to 2 kilograms of food and water per person per day. That's 2 to 4 pounds. Over 900 days, even on the low end, that's 900 kilograms per person, close to a metric ton just in food and water. For 4 to 6 people, you're already talking several tons of consumables. And that's with very conservative no-waste planning. And before we talk about oxygen, you can reclaim some water from humidity and urine, you can recycle some oxygen from exhaled carbon dioxide, but current systems don't get you to 100%. Even with aggressive recycling, you still have to launch a big reserve of water, food, and oxygen, plus the hardware that performs all the recycling, plus backup gear for when the first unit breaks. Then add all the other basics. You need medical supplies, tools, spare parts, clothing, sanitation hardware, computers, communication equipment, radiation shielding, exercise machines to keep your muscles and bones from degrading in low G. You need tanks, pipes, filters, wiring, batteries. Each of these things is not that heavy by itself, but add them up across 2.5 to 3 years and you're easily in the range of tens of tons of total payload and consumables for a serious crewed mission. So if mass is killing you and you can't just cut the mission down to a week on Mars, how do you fight back without magic technology? One big lever is to stop thinking in terms of one giant everything-in-one-shot rocket and start breaking the problem into pieces, reuse, and refueling. One of the most powerful tricks you have is simple in concept, but complex in operations. Launch fuel separately and refuel in orbit. Instead of loading all the propellant you'll ever need onto the same vehicle that has the crew cabin and life support, you launch tanker missions that carry almost nothing but fuel. Those tankers meet your main ship in low Earth orbit, transfer propellant into its tanks, then either deorbit and land for reuse or burn up in the atmosphere. That spreads the mass over several launches. Your main ship doesn't have to be strong enough to survive atmospheric ascent with all the fuel it will use for the Mars transfer already on board. You still pay the energy cost to lift that fuel into orbit, but you can use optimized tanker rockets for that, and you can launch them whenever the schedule allows, then fill the main ship over time. It turns a single hero launch into a campaign of launches, dockings, and transfers, but if you get it right, your cost per mission drops dramatically over many missions. Another lever is much more psychological as in engineering. Stop insisting that the first crew carries everything they will ever need. You don't want your astronauts to show up to a blank rock. You send cargo first. If you can land uncrewed vehicles on Mars in the right area, you can ship tens of tons of equipment, habitats, power systems, and raw materials ahead of time. Cargo doesn't complain if the trip takes 10 or 12 months instead of 6. Cargo doesn't care if the landing profile is a bit riskier. You can use slower, cheaper trajectories, higher G-loads, more aggressive aero braking, and less redundancy. You can afford to lose one out of several cargo landers, as long as enough of them arrive. That lets you build up a stockpile on Mars so that when humans finally land, the habitat shells, the initial power units, maybe even the ascent fuel plant are already there, tested and running. That strategy shrinks to crude stack. The human-rated ship now mainly has to carry the people, their immediate survival supplies, and maybe a limited set of critical spares. The heavy, bulky gear can go ahead of them. This doesn't make the rocket equation disappear, but it stops you from trying to stuff an entire colony into the same payload that has to keep people alive during the transfer. And all of that points at a brutal design philosophy. If you want to beat the mass problem, you have to think more like someone designing a submarine than someone designing a cruise ship. Every cubic meter you decide to pressurize is a commitment. That volume has to be built on Earth, hauled into orbit, accelerated to Mars, shielded against radiation and micrometeoroids, heated when it's cold, cooled when it's in sunlight, ventilated, monitored, and maintained for years. So when you look at early Mars habitat designs that show big, open, hotel-like spaces, those are more marketing images than serious engineering. In reality, you want compact multi-use modules, tight corridors, bunks that fold or stack, storage tucked into every spare corner. Life support racks, cables, and pipes crowd walls and ceilings. You want systems that are modular so you can remove and replace panels and components easily, but you don't waste mass on aesthetics. You also have to think hard about what happens when something fails. Redundancy is essential, but redundancy costs mass. Do you pack 3 of every critical component, or one main unit plus a pile of generic spare parts and tools so you can repair and improvise? Do you bring a whole extra pump, or extra seals, bearings, and a 3D printer that can make brackets and housings? Those choices have real mass and risk implications. So by the time you finish a serious mass budget for a Mars mission, you're in a constant fight. Cut 1 kilogram here, accept 1 kilogram there, always weighing comfort, safety, and performance against the rocket equation. There is no free luxury. A slightly larger window, a bit more headroom, a heavier chair might seem trivial on Earth, but in this context, each of those things ripples down into extra fuel, larger tanks, stronger structures, more launches, more cost. And even if you win that fight on paper, of course, the numbers are still tight. That's why the next question hits even harder. If keeping a small crew alive already forces this kind of ruthless design, what does it actually take to close the life support loop, recycle air and water, and keep human bodies functioning for 900 days in deep space and on Mars, when there is no way to bail out if the system starts failing? How do you keep a group of humans alive for about 900 days when the nearest store, hospital, and hardware shop are all tens of millions of kilometers away and nothing can reach you in time if something breaks? That's the core Mars problem, underneath the rockets and the orbits. You don't just need a ship, you need a closed little world that can run almost by itself for years. The first thing you have to accept is this. You cannot afford to throw things away the way we do on Earth. If you try to bring fresh air, fresh water, and fresh food for every single day with no recycling, the mass would be insane. So you go to a closed-loop life support approach. That means instead of treating water, air, and waste as single use, you treat them as cycles. Right now, systems like the ones on the International Space Station can already do part of this. They can recover roughly 90% of the water the crew uses by capturing humidity from the air, treating urine, and filtering it back to drinking quality. For oxygen, they can reclaim maybe 50 to 60% from exhaled carbon dioxide and waste. That is good enough for low Earth orbit, where a cargo vehicle can come up every few months with more supplies. For Mars, that level of closure is not enough. With a 900-day mission and launch windows every 26 months, you cannot rely on frequent resupply. You want those recovery numbers to be as high as you can practically make them, and you need them to work not for months, but for years, without full Earthside maintenance. That means more advanced hardware, more redundancy, and more careful monitoring of every part of the loop. Once you start closing loops, breathing becomes chemistry instead of just open a tank. The crew is constantly exhaling carbon dioxide. If you did nothing, CO2 would build up to toxic levels. So you scrub it out of the air and then decide what to do with it. One option is to use chemical scrubbers that bind the CO2 and then get regenerated by heat or pressure changes. Another option is to feed that CO2 into systems that split it into useful parts. Electrolysis can split water into oxygen and hydrogen. Combine that with reactions like the Sabatier process, where you take CO2 and hydrogen and turn them into methane and water, and you start to get a toolkit. On the ISS, the oxygen generation system can produce around 9 kilograms of oxygen per day, roughly 20 pounds. That's enough to support a moderate-sized crew. For a Mars habitat with 4 to 6 people, you'd need similar or higher capacity, plus backup units. So the air you breathe is not just from a tank, it's the output of machines that constantly split molecules, recombine them, and feed oxygen back into the cabin atmosphere. Those machines need power, filters, sensors, pumps, and careful control. They can clog, they can leak, they can drift out of calibration. Keeping your oxygen stable becomes a 24/7 chemistry and maintenance job. Water is similar and just as unforgiving. A human typically needs about 2 to 3 liters of drinking water per day. That's about 0.5 to 0.8 gallons. But total water use, once you add hygiene, food preparation, cleaning, and some technical uses, can be 10 times that if you're not careful. In a Mars mission, you don't have that luxury. You push recovery hard. You capture sweat and breath, you recycle urine, you condense moisture from the air, you filter, distill, and disinfect. With good recovery systems, you can push the net daily consumption down to under 1 liter per person per day, about a quarter of a gallon, maybe less. That sounds small, but over 900 days, even at 1 liter net per person, you're looking at hundreds of liters of water per astronaut, and that's after aggressive recycling. Multiply that by the crew count, and you see why every leak, every crack, every bad seal is a serious event. You can't just lose a bit and ignore it. Then comes food, which is harder to loop. You can recycle air and water with machines, but turning waste back into useful calories at high efficiency is much tougher. Right now, we do not have compact systems that can fully close the food loop in a small spacecraft. Plants can help, but you need light, space, nutrients, and time, and even then, you're not at 100%. So for the foreseeable future, a big chunk of your food still has to be shipped. At around 1.5 to 2 kilograms of food per day, that's 3 to 4 pounds, one astronaut will eat more than 1,000 kilograms of food across 900 days, over 2,200 pounds. For a crew of 4 to 6 people, that's several tons of food. You can cut that by choosing very calorie-dense, low-packaging meals, freeze-dried and vacuum-packed. You can pre-position food caches on Mars before the crew ever launches. You can grow some fresh vegetables in small greenhouses to supplement and improve nutrition and morale. But the core fact remains, you're shipping literal tons of calories from Earth. And the menu is not a trivial detail. Over years, nutrition gaps add up, and psychological fatigue from eating the same thing over and over is real. So you're balancing shelf life, mass, variety, and nutrition, and you have to plan it all up front. There is no supermarket run if you forgot something. All of these systems, air, water, food, sit on top of the same brutal rule. There is no safe failure. If a CO2 scrubber fails on day 120, you can't pull over and wait for a tow. If a pump in the water processor seizes, or a filter clogs, or a sensor lies, the crew has to diagnose and fix it with the tools and spares they already have. That means every critical subsystem needs backup. Often, you don't just bring one unit, you bring a second unit, plus spare parts, plus a lower-tech emergency mode you can fall back on. That redundancy adds mass and complexity. But without it, the mission is fragile. You might, for example, have a main CO2 removal system that is efficient but complex, and a more primitive cartridge-based system you can switch to if the main one fails, even if it's less efficient and uses consumables. You might have multiple water loops, so contamination in one doesn't take down the whole system. You design for failure, you expect things to break, and you give the crew enough options to patch the system together until the end of the mission. On top of that, the crew has to be trained to a very high level, not just to operate these systems, but to repair them under pressure. They need to be part mechanic, part plumber, part electrician, part chemist. The interfaces have to be understandable. The diagnostics have to be clear. The documentation has to be usable when you're tired, stressed, and maybe dealing with a slow leak somewhere else in the habitat at the same time. So by the time you've laid out the full life support design, you're not just moving people, you're moving a small, tightly controlled ecosystem built out of metal, plastic, fluids, and software that has to run for years with no outside help. And even if you manage that, even if your air, water, and food are stable, there's a bigger, invisible problem waiting outside the hull: constant radiation from deep space that your body has never evolved to handle for this long. Even if you lock down air, water, and food, there's something you can't see that's hitting you non-stop between planets: radiation. On Earth, you have a thick atmosphere and a strong magnetic field protecting you. In deep space, you lose both. Your spacecraft's hull becomes the only barrier between your cells and high-energy particles that can damage DNA, increase cancer risk, and mess with your nervous system over time. Out there, you're dealing with two main sources. First, galactic cosmic rays. These are high-energy particles, mostly protons and heavier nuclei that come from outside the solar system, accelerated by things like supernova explosions. They are always there, a constant background, coming from all directions. They're very energetic and very penetrating. They can punch through a lot of material before stopping. Second, you have solar energetic particles, bursts of high-energy protons and other particles thrown out by the sun during solar flares and coronal mass ejections. These don't hit you all the time. They come in events. Most of the time, solar particle levels are relatively low. Then a big eruption on the sun happens, and in a matter of tens of minutes to hours, the particle flux can jump by orders of magnitude. These events can deliver a dangerous dose if you're unshielded. So what kind of doses are we really talking about? On the International Space Station, astronauts typically get about 80 to 160 millisieverts of radiation over a 6-month mission. That's already several times higher than the average yearly dose on Earth's surface. But it's still cushioned by Earth's magnetic field, and they're only up there for months, not years. Now stretch that out to a Mars round trip. In deep space with standard aluminum hull shielding, you might be looking at total mission doses in the range of 500 to 1,000 millisieverts, half to 1 sievert, possibly more depending on solar activity and mission duration. Around 1 sievert total, you are not talking about immediate sickness, but you are significantly increasing long-term cancer risk. Some estimates suggest a noticeable percentage increase in lifetime cancer probability at that level. For astronauts who have already accepted elevated risk from low Earth orbit missions, this is an extra step up. Shielding sounds like the obvious answer. Add more material between the crew and space. But shielding is not magic. And again, mass comes back to hit you. Different types of radiation interact differently with matter. For the relatively lower energy particles in many solar events, hydrogen-rich materials work well. Water, polyethylene plastics, and similar materials can slow and absorb these particles effectively. That's why people talk about using water tanks, food stores, or dedicated plastic blocks to surround a small storm shelter in the spacecraft. You might design an inner room with walls equivalent to around 20 grams of material per square centimeter, which translates to several tens of centimeters of water or plastic, where the crew can move during a strong solar storm. If a big flare is detected, everyone goes into that shelter for a few hours or maybe a day until the worst of the particle flux passes. That can dramatically cut the dose from solar energetic particle events. But for galactic cosmic rays, the story is worse. These particles have such high energies that as you make the shielding thicker, you start to see diminishing returns. They can punch through a lot of material, and when they collide with atoms in the shielding, they can create secondary particles, which also contribute to dose. To truly block a large fraction of GCRs, you would need so much mass around the habitat that the spacecraft would become unrealistically heavy to launch. So you don't eliminate GCR exposure, you mainly try to reduce it to a level you're willing to accept, and limit how long the crew is out there. Because passive shielding is so limited, people have looked at more advanced ideas, like creating artificial magnetic fields around the spacecraft, or using plasma structures to deflect charged particles, basically trying to build a mini magnetosphere. On paper, these concepts can reduce some of the particle flux without adding massive amounts of material. In practice, they require large power, complex hardware, and a lot of testing before anyone trusts them on a mission where human lives are at stake. Right now, none of these active shield systems are anywhere near standard flight hardware for deep space crews. For the first Mars missions, the realistic tools on the table are material shielding in smart layouts, mission design that keeps travel time as short as reasonably possible, and careful monitoring of the sun so you can get the crew into a storm shelter before the worst of an event arrives. That's not comforting, but it's honest. And then there's the part we really don't know yet. What multi-year exposure to this mixed radiation environment does to the human body beyond cancer risk. We have data from ISS crews on 6-month missions, some a bit longer, in low Earth orbit. We don't have data for 2.5 to 3 years in deep space, with no magnetic field and continuous exposure to GCRs. Radiation doesn't just cause cancer. It can affect the cardiovascular system, increasing the risk of heart and blood vessel problems. It can impact the brain, potentially altering cognitive function, memory, and mood. It can damage the eyes, leading to cataracts. There are animal studies and cell studies that suggest all of this is possible, but they don't fully map to what happens to a small group of adults in deep space over years. So when you send a crew to Mars, you are, in a very real sense, putting them into a radiation experiment that has never been run at human scale. You can estimate, you can model, you can simulate, but you don't actually know the full spectrum of health effects across a whole mission. You're asking them to accept a risk profile that goes beyond what any astronaut has taken on so far. And even if they manage to ride out that radiation environment with storm shelters and careful mission timing, there's another problem you can't turn off: gravity. Or more specifically, the lack of it. Your body evolved in Earth's gravity, and when you take it away for months, muscles, bones, circulation, even your sense of balance start to change in ways that are still not fully understood. Then, after all that, you drop the crew into only 0.38 G on Mars and expect them to work. Your body evolved to live at 1 G, on solid ground with a clear up and down. A Mars mission breaks all of that. First, by putting you in microgravity for months, then dropping you into 0.38 G and expecting you to work like a construction worker and a scientist at the same time. The problem isn't just comfort, it's whether your bones, muscles, heart, and brain can actually handle that sequence without failing in the middle of the mission. Look at what we already know from the ISS. In microgravity, if astronauts do not exercise, they can lose around 1 to 2% of their bone mass each month. That's like developing osteoporosis at fast forward. Leg muscles, back muscles, and postural muscles weaken quickly because they're not supporting your weight anymore. Even with strict exercise plans, more than 2 hours a day of resistance and cardio training, crews still see losses in bone density and strength. So, on the way to Mars, during that 6 to 9 month cruise, the crew can't just rest and wait. They have to treat exercise almost like a life support function. You need treadmills with harnesses to pull you down, cycle ergometers, and resistive devices that simulate lifting weights, all in a cramped spacecraft, all running daily. Those machines vibrate, they wear out, they need maintenance, and they take up mass and volume. You pay for every bar, piston, and bearing and launch cost. But if you skip them, you arrive at Mars with deconditioned, fragile bodies that might not even be able to walk in 0.38 G, let alone do heavy work in a suit. Even with all that effort, you don't perfectly cancel the damage. Astronauts often come back to Earth needing rehabilitation with changes in balance, muscle coordination, and cardiovascular response. For a Mars mission, there is no rehab phase before you go to work. You land, your spine and joints have been floating for months, your heart has been pumping in microgravity, your blood has redistributed, and now you suddenly have weight again, even if it's lower than on Earth. You have to climb ladders, move equipment, operate in a bulky suit, maybe deal with an emergency on day one. So you start thinking, is there a way to avoid spending so long in microgravity at all? That leads straight to artificial gravity. In principle, you can spin a spacecraft or a part of it so that centrifugal acceleration pushes you toward the floor, mimicking gravity. The faster you spin, or the larger the radius of the spin, the stronger the effect. For Mars missions, one idea is to aim for artificial gravity close to Mars' surface gravity, about 0.38 g, instead of full Earth gravity. If you have a rotating structure with a radius of about 50 meters, roughly 164 feet, you need a rotation rate of around 1.9 turns per minute to get that level of artificial gravity at the rim. That spin rate is slow enough that most people could probably adapt without severe motion sickness, and the radius is big but not absurd in space terms. The problem is building it. Right now, no one has flown a large, human-rated centrifuge in orbit, let alone use spinning habitats on an interplanetary ship. You need a structure strong enough to handle constant tension, bearings or joints that can run for years, and a way to manage fluids, air, and docking in a rotating frame. You also have to deal with Coriolis effects inside, where moving your head or arms can create strange sensations because the rotation interacts with your motion. All of that is engineering we still need to test and practice before we trust it on a mission that lasts several years. Let's say you solve at least part of the microgravity problem with hardcore exercise and possibly some artificial gravity during the transit. You still hit a huge unknown the moment you land: partial gravity. Mars gravity is about 1/3 of Earth's. That number sounds simple, but biologically, we have almost no data on what long-term life in 0.38 g actually does to a human body. Does 0.38 g stop bone loss or just slow it down? Do muscles stabilize at a new normal or keep degrading just at a reduced rate? How does your cardiovascular system adapt when it doesn't have to push blood as hard as on Earth, but more than in microgravity? What happens to balance, coordination, and inner ear function over a year and a half in that environment? We don't know. We have data for full gravity on Earth, and we have increasing data for microgravity in orbit, but almost nothing in the in-between zone. The only way to find out is to send people and measure, which means the first crews to Mars are not just explorers, they are also experiments. They will be scanned, sampled, monitored, and compared across the mission to see how human physiology behaves in partial gravity. That adds another layer of risk because you can't guarantee in advance that 0.38 g is good enough to prevent serious long-term issues. Physical stress is only part of the story. A Mars mission also pushes hard on the mind. On Earth, we've already seen what isolation and confinement do in places like Antarctic bases during winter, and then simulated Mars habitats where small crews live together in sealed spaces for months. The pattern is clear. People experience increased stress, sleep problems, mood swings, and conflicts even when they know they can call for help and, in the worst case, be evacuated within days. Now extend that to Mars. You're in a small group, likely 4 to 6 people, in a limited volume for years. Outside the walls is a cold, low-pressure environment that kills you in seconds without a suit. You know that real-time conversation with Earth is impossible, and that messages can take up to 22 minutes one way, depending on where the planets are. That means if you send a question, you might wait nearly 3/4 of an hour for a full back and forth. Every argument, every misunderstanding, every decision has to be handled with that lag in mind. You can't escape your crewmates, you can't really be alone, but you also can't get away. Noise, smell, lack of privacy, routine, and constant awareness of risk all pile up on the brain. Sleep cycles can drift, especially if lighting and work schedules aren't tightly controlled. Small tensions can grow if they aren't recognized and managed early. That's why crew selection, training and conflict resolution, and psychological support aren't soft secondary issues. They're central to survival. Then add one more layer of tension. What happens when someone gets seriously ill or injured? On Earth, if you have an appendicitis, a heart attack, a complicated fracture, or a severe dental infection, you go to a hospital that has surgeons, imaging, blood banks, and a whole support staff. On Mars or during the transit, none of that exists. There is no emergency evacuation option. You can't load someone on a return ship and get them home in time. At best, you have a small medical bay, a short list of tools, maybe portable imaging equipment, and 1 or 2 crew with advanced medical training. If they hit a problem they haven't trained for, they can ask Earth for advice, but that advice comes with a delay that can stretch to 20 minutes one way. So your doctor might be trying to stabilize a patient with incomplete tools while listening to audio instructions or reading text that arrived half an hour after they asked for it. That applies to surgery, serious infections, allergic reactions, mental health crises, and any unexpected condition. You can prepare for a lot of scenarios. You can stock broad spectrum treatments, but you can't cover everything, and you can't fall back on "we'll get them to a hospital." The crew and their limited equipment are the hospital. All of this, the microgravity damage, the unknowns of partial gravity, the psychological strain, and the medical vulnerability, stacks on top of the radiation risk you already carry. You're not just fighting one stressor, you're running a multi-year experiment on human limits, while asking the same people to perform complex, high-stakes engineering and science the entire time. And even if the crew's bodies and minds hold up under all of that, the mission is still not safe, because eventually they have to do one of the hardest things in spaceflight: land a large, heavy vehicle on a planet with air too thin to slow you down properly, but thick enough to heat you up violently on the way in. How do you land a huge, multi-ton spacecraft on a planet where the air is just thick enough to heat you up violently, but too thin to actually slow you down properly? That's the Mars entry problem in one sentence, and it's why 7 minutes of terror for a 1-ton robot turns into half an hour of non-stop risk when you scale it up for humans and full-size habitats. Start with the basic environment you're slamming into. Mars has an atmosphere, but at the surface, it's less than 1% of Earth's sea level pressure. It's mostly carbon dioxide, it's cold, and it's thin. At high speed, it's thick enough to generate serious aerodynamic heating on your heat shield, so you can't ignore it. But when you want to slow a really heavy lander, that same thin air doesn't give you enough drag. Parachutes, which work brilliantly on Earth, become weak tools on Mars if your vehicle is too massive. You get the worst of both worlds, heating without easy braking. So look at what actually happens when a Mars ship arrives. You're coming in on a hyperbolic trajectory relative to Mars, basically falling toward the planet. By the time you hit the upper atmosphere, you're moving at around 5.5 to 7.5 kilometers per second. That's about 12,000 to 17,000 miles per hour. At those speeds, the air in front of your heat shield gets compressed and heated to extreme temperatures. The shield itself can see temperatures above 1,500 degrees Celsius, over 2,700 degrees Fahrenheit. The scary part is how sensitive this phase is. Small changes in the atmosphere can shift everything. If the air is a bit denser than you expected, or dust levels are higher or lower than your model, your drag profile changes. That means your trajectory through the atmosphere changes. A tiny difference high up can translate into missing your target area by kilometers on the ground. On top of that, the heat load on the shield changes with angle, speed, and density. You have to ride a narrow corridor. Too steep and you burn and overheat. Too shallow and you skip or crash long. For the robotic landers we've sent so far, the sequence is brutal but manageable. They come in with a heat shield, slow down using the atmosphere, then deploy supersonic parachutes while they're still going faster than the speed of sound. The parachutes drag them down further, then they cut the chute and use retro rockets to slow the last bit, sometimes with a crane-like system lowering the rover on cables. That whole chain has worked for payloads around 1 ton. It's still risky, but we've done it. Now scale that up. A human lander, even a minimal one with crew, life support, fuel reserves, and descent hardware, might mass 20 to 40 tons or more. Parachutes do not scale nicely to that kind of mass in thin air. You'd need enormous canopies, dealing with insane forces at deployment in a dusty, uncertain atmosphere. There's a practical limit where parachutes simply cannot provide the drag you need in time. So that pushes you to another tool: supersonic retro propulsion. That means lighting rocket engines while you're still going at supersonic speeds in the atmosphere, using thrust to do a huge fraction of the braking that parachutes would handle on Earth. You still use a heat shield to survive the initial entry, but instead of depending on parachutes to carry most of the load, your engines start firing while the flow around you is still supersonic. This is technically possible. We've already used retropropulsion in Earth landings with reusable boosters, but doing it on Mars at that scale, in that atmosphere, with humans on board is a different level of challenge. Engines have to work perfectly after months in space. The guidance system has to control a falling, firing vehicle through chaotic airflow and dust. The engines, their exhaust, and the surrounding gas flow all interact in complex ways that you have to test and understand before you trust them over a Martian landscape. And it's not enough to just get down somewhere. For a serious Mars mission, you have to land near very specific pre-positioned assets. You will have sent habitats, power units, maybe fuel production plants, and supplies ahead of the crew. When the human lander comes in, it needs to touch down within maybe a few hundred meters of that existing base. The crew cannot walk tens of kilometers across rough terrain in suits, dragging critical gear, hoping dust storms don't hit them on the way. So now your entry, descent, and landing system has to deliver both survival and precision. You have to ride that narrow entry corridor, survive heating, deploy whatever drag devices you have, manage supersonic retropropulsion, and still steer the vehicle into a specific landing ellipse that is much smaller than the ones we accept for robotic missions. Making that worse, Mars is not a clean paved runway. You're dealing with rocks, slopes, dust, and limited high-resolution mapping. We have good orbital images for candidate landing sites, but not centimeter-level detail everywhere. A big boulder, a hidden ditch, or a slope beyond design limits near your touchdown point can tip or damage the lander. So you need terrain relative navigation, sensors that look down during descent, recognize landmarks, and adjust your trajectory on the fly to pick a safe spot within your designated area. That's more software, more sensors, and more things that have to work during the most stressful minutes of the mission. And even if you get the guidance right, you still have to think about what your engines are doing to the surface. When you fire powerful rockets close to the ground in low gravity, in loose soil, you don't just blow away a bit of dust. You can launch regolith at high speed sideways, basically creating a spray of sand and rocks. That plume can sandblast nearby hardware, damage solar panels, abrade habitat walls, and bury or uncover cables and equipment. If you've already landed structures close by, the last thing you want is a new lander blasting them with debris. That's why people talk about building landing pads on Mars, either by pre-landing robotic systems that flatten and harden a surface, or by choosing sites and approach paths that minimize plume damage. But you can't build those pads without landing something first, so you're stuck in a loop, needing safe landings to build safer infrastructure. All of this makes the scaled-up 7 minutes of terror for humans more like a whole chain of critical events, any one of which can end the mission. The heat shield has to survive and detach properly. The guidance has to stay locked on. The engines have to start on time and not choke on dust. The navigation system has to see the ground and make good choices. The touchdown hardware has to handle uneven terrain, maybe with crushable legs or adjustable suspension. There's very little room for partial success. And even if you land cleanly without tipping or breaking legs, the story doesn't relax because now the crew has to step out into an environment that will kill them in minutes without a suit, set up their new home, and start building a base on a world that is freezing, low pressure, dusty, and constantly trying to leak heat and air out of everything you brought. Once you get a crewed lander onto Mars in one piece, the hard part shifts from don't die in the next 10 minutes to don't die in the next 900 days. So what does it actually mean to build a home on this planet? Not in artist's renders, but in real hardware, mass, and risk. First problem, temperature. Mars is cold all the time. The average surface temperature is around minus 63 degrees Celsius, about minus 81 degrees Fahrenheit. Near the equator at local midday, you might briefly creep just above freezing on a good day, but as soon as the sun drops, the heat vanishes. Nighttime temperatures can plunge below minus 100 degrees Celsius, about minus 148 degrees Fahrenheit. That means the outside world is not just chilly, it is a deep freeze. Your habitat has to fight that. It needs insulation in every wall, floor, and ceiling. It has to be pressurized so you have air to breathe, and actively heated so your internal temperature stays in a narrow band where humans and electronics both like to live. Any heat you generate wants to leak outward into that cold environment. Every window, every hatch, every cable feed through becomes a potential path for energy loss. So your power system is constantly working just to keep the inside from sliding toward outside conditions. You're not heating a single room, you're heating an entire sealed volume, 24/7 through long winters and dust storms that block sunlight for days or weeks. If the heaters quit or power drops too low, the temperature inside will start falling and all the life support you worked so hard to build gets slower, less reliable, and eventually stops. If you have to fight that temperature difference, what does the pressure difference do to your structure? On Earth, at sea level, ambient pressure is about 101 kilopascals, roughly 14.7 pounds per square inch. On Mars, surface pressure is around 600 pascals, about 0.09 psi, so basically almost vacuum. Your habitat will probably run at something like 50 to 70 kilopascals inside, around 7 to 10 psi, with higher oxygen fraction than Earth air. That makes every habitat module a giant rigid balloon. Inside, the air is constantly trying to expand outward. The hull, the joints, the windows, and the seals are all holding back that force. Any rupture, any serious leak is an emergency. It does not matter if the hole is from a micrometeoroid, a dropped tool, a bad weld, or a manufacturing defect. The result is the same. Air rushes out, pressure drops, and you have minutes to isolate that volume or patch it. So the base layout has to include airlocks, isolation valves, and doors that can be sealed quickly. You can't have long, open hallways with no breaks. You want compartments that can be shut off if there's a problem, so a leak in one module does not drag down the whole station. Every time you move between inside and outside, you go through controlled decompression and recompression, because losing a few kilograms of air on each EVA, each spacewalk, adds up over hundreds of days. Even if you keep the air and heat inside, there's still the radiation that hammered you during transit. The thin Martian atmosphere and lack of a global magnetic field mean you're still getting hit on the surface, just at a reduced rate compared to deep space. How do you push that down further without shipping ridiculous amounts of shielding from Earth? One answer is to use what Mars already has, its soil. The top layer of dust and crushed rock, the regolith, is not friendly to lungs or machinery, but it's mass, and mass blocks radiation. If you bury your habitats with about 2 to 3 meters of soil, roughly 6 to 10 feet, you can cut the radiation dose significantly. You're basically using Mars itself as a protective blanket. But that means moving a lot of material. Even covering a modest habitat, say tens of meters long, with a couple of meters of soil means pushing around hundreds of tons of dirt. Doing that by hand in suits is not realistic. You need excavation robots, bulldozer-like machines, or conveyor systems that can operate in low pressure, low temperature, and dust for long stretches. Another approach is to land inflatable structures, expand them, and then quickly cover them with regolith using pre-landed robotic equipment, so you get large volume plus shielding with less shipped mass. Either way, you are not just dropping a can on the surface and calling it good, you're building a partially buried outpost. Let's say you get the shell and shielding right. What is life like inside that protected bubble? The rules inside look a lot more like a submarine or a spacecraft than a house. You manage the air chemistry continuously. Carbon dioxide scrubbers pull CO2 out of the air. Humidity control systems stop moisture from condensing on cold surfaces, where it can cause corrosion or mold. Fans and ducts move air so you don't get dead spots where CO2 or heat can build up. You aim to keep CO2 levels well below about 5,000 parts per million for long-term exposure, because above that, people's thinking gets slower, headaches and fatigue increase, and performance drops. On Earth, in a building, you can open a window or increase outside airflow. On Mars, there is no outside air. All the air is recycled and recirculated, so filters, scrubbers, and monitors have to work all the time. Any sensor that drifts, any pump that fails, any clogged filter can quietly push the atmosphere out of its safe band. Noise and airflow patterns matter more than you think. Fans hum constantly. Air jets can be uncomfortable if they blow directly at workstations or sleeping areas. You have to balance airflow for life support with basic habitability, so people can sleep and work without constant distraction. Temperature gradients inside, drafts near bulkheads, and hotspots near equipment racks all show up in daily life. Then there's the question of size. When people picture a Mars base, they often see something sprawling. In reality, your first base is small. You might have a few connected modules totaling maybe 150 to 300 square meters of usable floor area, roughly 1,600 to 3,200 square feet, for the entire crew. That's not one big open space. It's split across labs, bunks, a small galley, storage, airlocks, and equipment bays. Personal cabins may be just a few cubic meters each. Every part of that interior has to be designed for maintenance. Wall panels can't just be decoration. They cover pipes, cables, ducts, and racks. You need to be able to open them, swap a valve, reroute a line, or pull out a failed electronic unit. Filters have to be reachable and replaceable. Power electronics need access for testing and repair. You can't rely on a factory or service center. Everything is either replaced from spares you brought or fixed with tools and raw stock on site. Modularity becomes survival strategy. You want standard interfaces between modules, so you can add a new lab, another habitat, or a greenhouse without redesigning the whole base. You want standard connectors for power, data, fluids, and air, so one spare part can fix multiple systems. The base has to be expandable, because if the first missions work, more crews and more hardware will arrive. But the original core also has to be repairable for years, because sending an entire new base is too expensive. You also need the ability to isolate sections quickly. If there's a fire in one module or a serious leak, you shut hatches, cut lines, and keep the rest of the base alive. That means redundancy in pathways, so air, power, and data can be rerouted around damaged segments. It means planning not just for everything is fine, but for this room is gone, how do we keep going? And underneath all of this, one question is always running in the background. Even if your walls hold, your air stays clean, and your crew can live in that tight, buried habitat, how do you keep the power flowing day after day through winter nights and dust storms that can cut sunlight by 90% on a planet 1.5 times farther from the sun than Earth? How do you keep a base alive when the sun itself is weaker and sometimes disappears behind dust for weeks, but your heaters, pumps, scrubbers, and computers can never shut off? That's the power problem on Mars, and if you get it wrong, everything else you built is only temporary. Start with the basic fact. Mars is farther from the sun, about 1.5 times Earth's distance. That means the sunlight that actually hits the ground is weaker. At Earth's orbit, you get roughly 1,360 watts of solar power per square meter at the top of the atmosphere. At Mars, that number is closer to 590 watts per square meter, so basically working with 43% of the energy per unit area. By the time that light goes through the thin Martian atmosphere and hits your panels, you're already behind compared to Earth orbit or the moon. The same panel that gives you a certain power level near Earth will give you less on Mars, simply because less solar energy arrives in the first place. Now layer dust on top of that. Mars is famous for dust storms, from local ones that last days to global events that can wrap the whole planet and linger for weeks. During those storms, the sunlight reaching the surface can drop by 50 to 90%. So your power source is not just weaker, it's variable, and sometimes it falls off a cliff. So if you want to lean on solar power, you compensate with area. You lay out large solar farms, hundreds to thousands of square meters of panels spread around your base, on the ground, or maybe on simple frames. With decent efficiency, that can give you tens of kilowatts under good conditions, enough to run life support and some extra systems. But those panels sit in low pressure, low temperature, and constant dust fallout. Dust is not a small cosmetic issue, it's a performance killer. Even a thin layer, around a millimeter thick, can noticeably cut output. Over time, dust accumulates on the glass or polymer fronts of the panels, scattering light and blocking it from reaching the cells. If you do nothing, your solar farm slowly fades. So you have to plan dust management as a core part of the power system, not a late add-on. You can go a few ways. One is mechanical, robotic wipers that move across the panel surfaces, brushing dust off, like large, slow windshield wipers. Another is fixed brushes that panels can tilt and push against. You might also use crew with hand tools, but sending people out in suits just to clean panels is time-consuming and risky, especially during harsh weather. More advanced ideas include electrostatic cleaning, where electric field and vibrations help shake or push dust off surfaces. Each of these systems adds complexity, moving parts, and failure modes, but without some form of active cleaning, big solar fields on Mars will degrade quickly. Even if your panels are clean and the sun is shining, you still have to deal with night. A Martian day, a sol, is about 24.6 hours, close to an Earth day. That means you have around 12 hours of darkness to ride through, give or take, every single sol. During that time, solar panels provide zero power. But your base can't pause. Life support, thermal control, and critical systems must keep running. That forces you to add energy storage, usually batteries or some other storage like regenerative fuel cells. For early missions, it's reasonable to assume each habitat and its attached systems might need tens of kilowatt hours of stored energy to get through the night, similar to several electric car battery packs per habitat. Scale that to a full base with multiple modules, greenhouses, and processing plants, and you're looking at very large battery banks with all the associated mass, temperature management, and degradation issues. Batteries don't like extreme cold, so you have to keep them in controlled environments. They also wear out over time, losing capacity. If your mission runs for years, your storage system will slowly decline in performance, unless you ship replacements or build in significant extra capacity from the start. Every decision here loops back to mass and launch cost. To get around the dependence on sunlight and daylight cycles, you look at another option: nuclear reactors. A compact fission reactor doesn't care if it's day or night, clear sky or dust storm. Once it's running, it can produce a steady stream of electrical power and waste heat 24/7 for years. Concepts on the table include reactors in the roughly 10 to 40 kilowatt electrical range per unit, designed to be buried or shielded and left to run with minimal intervention. That steady power is extremely attractive for Mars. It gives you a baseline you can rely on, powering life support, heating, and essential systems, while solar and batteries handle peaks and optional loads. The waste heat from the reactor can even help warm habitats or industrial modules, cutting your heating requirements. But nuclear power brings its own set of issues. You have to launch a reactor from Earth, and even if you ship it in a safe, non-critical state and only start it once it's on Mars, people will worry about launch accidents and contamination. You also have to manage shielding so the crew is protected from reactor radiation, and you have to plan for eventual shutdown and waste handling. None of these are unsolvable. We've flown reactors in space before, but when you had crew and long-term surface operations, the design has to be extremely robust and acceptable. When you try to put real numbers on a Mars base, the power budget gets serious fast. Life support alone, air circulation, CO2 removal, water processing, and general electronics can easily take several kilowatts. Heating, especially in cold seasons and at night, can add a lot more, depending on how well insulated everything is. Communications back to Earth, running high-gain antennas and transmitters, is another slice. Then you add ISRU systems, in situ resource utilization, machines that turn Martian air and ice into oxygen, water, and fuel. Those are essentially industrial plants running compressors, reactors, pumps, and freezers. They can easily demand multiple kilowatts each, sometimes tens of kilowatts if you want to produce significant amounts of propellant or water over reasonable timeframes. Scientific equipment, rovers, construction gear, and computing clusters for data processing stack even more on top. It's very easy to reach a total requirement of tens of kilowatts continuous per base, not as a peak, but as a normal operating level. That's similar to running multiple suburban houses and a small workshop or factory at the same time, except you're doing it on another planet, with limited maintenance options and no grid to fall back on. If something in your power chain goes down, you don't just lose luxuries, you risk losing heat, air, and fuel production. So a real Mars power system is not one technology, it's a layered strategy. Solar for flexibility and scalability, batteries or other storage for night and short interruptions, nuclear for a solid backbone that ignores dust and darkness. You overbuild where you can, you design for failures, and you monitor everything constantly. Power management isn't a side task, it's as central as life support, because without it, life support dies. And even if you solve that, even if the lights stay on through storms and winters, you're still tied to Earth every time you need oxygen, fuel, or building materials, unless you start pulling those directly from Martian air and dirt. That's the next step, turning the planet itself into your supply line, or accepting that every kilogram you ever need has to ride a rocket from home. If you tried to run a Mars base only on what you brought from Earth, the rocket equation would crush you. So at some point, the question flips. Instead of what do we haul, it becomes what can we steal from Mars itself? That's what in situ resource utilization really is, turning the air and dirt around you into oxygen, water, fuel, and building material. So every kilogram you launch from Earth is doing something more valuable than just being raw mass. Start with the air, because even though it's thin and unbreathable, it's actually a gold mine. Mars's atmosphere is about 95% carbon dioxide, with a surface pressure of around 600 pascals, roughly 0.09 psi. That's not useful for lungs, but it's perfect for chemistry. With solid oxide electrolysis and related tech, you can pull oxygen out of that CO2. A small demonstrator has already done this, producing grams of oxygen per hour from Martian air. Scale that up with more power and larger units, and you're no longer just proving a point, you're filling tanks. That oxygen can do two things. It can feed your habitat life support, topping up cabin air and providing a local source so you don't rely only on preloaded oxygen reserves. And it can feed your rockets, because oxygen is the oxidizer in methane oxygen or hydrogen-oxygen engines. Every kilogram of O2 you make on Mars is a kilogram you didn't have to push up from Earth's gravity well. Next resource, water. You can't survive or make fuel without it. Orbital data and landers tell us there's subsurface ice on Mars, especially at higher latitudes, and indications of underground ice deposits even closer to the equator in some regions. That ice isn't nice, clear drinking ice. It's mixed with dust and rock, but it's still water locked in the ground. If you can dig or drill down to those ice layers, you can extract water by crushing the material and heating it, or by more advanced methods like subsurface melting. Even a layer of ice 1 meter thick, about 3 feet, spread under a modest area near your base can represent thousands of liters of water. That water can be filtered for drinking, used in hygiene, fed into electrolysis units to split into hydrogen and oxygen, and stored in tanks around habitats to serve as extra radiation shielding. Once you have CO2 from the air and water from ice, you have everything you need to start making fuel. That's where the Sabatier process comes in. You take carbon dioxide and hydrogen, run them over a catalyst at high temperature and pressure, and you get methane and water. Methane is a good rocket fuel, especially when paired with oxygen. The water produced in the reaction can be electrolyzed again, split back into oxygen and hydrogen. The hydrogen goes back into the loop, the oxygen goes into tanks, and the methane goes into separate tanks. With enough power, you can run this cycle continuously for months before the crew even arrives, slowly filling up a return vehicle's tanks on the surface. That way, you don't launch the ascent and return propellant from Earth at all. You land an empty or partially fueled return stage, plus the ISRU plant, let it sit there and work, and only send humans once you've confirmed that the tanks are full and the system is stable. That single change cuts mission mass massively, and it's exactly why fuel production on Mars is such a big deal in every serious mission plan. And you don't stop at fluids. The ground itself, the regolith, is your next target. Shipping bricks, beams, and blocks from Earth is ridiculous when the entire planet under your feet is made of material you can shape. Martian regolith is a mix of fine dust and larger grains and rocks. If you compress it into blocks, bake it, or sinter it using concentrated sunlight or electric heaters, you can make solid building elements. You can imagine large solar concentrators focusing light onto regolith, fusing grains together into slabs or tiles, or 3D printers that take regolith as feedstock, mix it with a binder, and lay down layers to form walls, arches, or shielding blocks. Instead of sending finished construction material, you send the machines, molds, and tools that transform local dirt into usable structures. Over time, that lets you build landing pads, berms, radiation walls, and even parts of pressurized tunnels without lifting equivalent mass from Earth. The big picture in all of this is closing as many loops as you can. The more you can pool locally, water, oxygen, methane, basic construction material, the more you can use Earth launch mass for things you genuinely can't make on Mars yet. That means complex electronics, high-precision instruments, advanced medical supplies, specialized alloys, and spare parts that require sophisticated factories. Every liter of water you don't ship can be replaced by a liter of coolant or a medical fluid you can't synthesize yet on Mars. Every kilogram of oxygen made from Martian air frees a kilogram of payload for extra batteries, better sensors, or more robust life support gear. Over multiple missions, the base shifts from camp that lives off supply drops to outpost that uses local resources to extend its reach. But there's a hard catch. None of this ISRU hardware is optional fluff. If your mission plan depends on locally produced oxygen and fuel, and the ISRU system fails, the crew's return ride becomes questionable. So you're back in redundancy territory. Multiple units, spare parts, backup modes, and lots of testing before you ever trust lives to that chain. And even if the ISRU plan to work and your storage tanks are full, your crew still has to get out there in suits and vehicles to set things up, to maintain drills and reactors, to lay cables and build structures, all while working in a low-pressure, dusty, cold environment. So the next question is, once you have a base on Mars and some local resources, how do you actually move, explore, and work on Mars day after day without a single mistake turning a routine EVA into a fatal incident? Once you have a base on Mars, you're not supposed to sit inside and stare at the walls for 500 days. You actually have to move around, explore, and build. That means you need a whole surface operation system that works in low pressure, low temperature, and constant dust. And you need it to work safely enough that routine trips don't turn into emergencies. The first piece is mobility. Walking around in a suit is fine for short distances near the habitat, but if you want to reach nearby hills, ice deposits, interesting geology, or future building sites, you need vehicles. Think of pressurized rovers as small trucks on steroids, not golf carts. They're sealed with their own life support, heaters and communication systems, running on battery packs or fuel cells, and they weigh several tons each. Those rovers have to handle rough terrain, rocks, soft dust, maybe slopes covered in loose material. Tires or tracks need to work at temperatures that can sit at minus 50 degrees Celsius, around minus 58 degrees Fahrenheit or colder. Materials can become brittle, lubricants can thicken or freeze, seals can crack. There's almost no air, so you can't rely on conventional cooling. Everything on the rover, from motors to electronics, has to be designed around vacuum-like conditions and extreme cold. Range matters too. A rover that can only go a couple of kilometers from the base is basically a local shuttle. For serious exploration, you want ranges in the tens to hundreds of kilometers, tens to hundreds of miles with safety margins. That means careful energy planning, charging infrastructure, or replacement battery packs and backup systems. Every excursion has to be planned with enough margin to get back, even if one motor fails or a route turns out rougher than expected. Next, suits. Even with pressurized rovers, you can't stay inside forever. You need to go out directly onto the surface to place instruments, fix equipment, dig trenches, connect cables, and run experiments. Mars dust is a big problem here. It's very fine, it gets into everything, and it's abrasive. On top of that, it likely contains perchlorates, chemically reactive salts that are not something you want in your lungs or eyes, or rubbing into seals and joints. Suit joints have to flex thousands of times over the mission, bending knees, elbows, wrists, and hips without grinding themselves apart with dust. That means complex bearing systems, seals, and covers all designed to keep the worst of the particles out. If dust builds up inside those mechanisms, friction increases, movement gets more difficult, and eventually the joint can seize or tear. If that happens outside, you're racing the clock to get back to an airlock. To cut down the risk of dragging dust inside the habitat, one idea is the suit port. Instead of storing suits inside, you dock them to the outside of the habitat. You open a hatch from inside into the back of the suit, climb in, seal yourself, then de-dock the suit and step out. When you come back, you dock the suit again and step into the habitat directly, leaving the dusty outer shell outside. That reduces internal contamination and makes cleaning easier. But it makes the interface between suit and hull absolutely critical, because a failure there is a direct path for vacuum into the base. Why go through all that just to step outside? Because with humans on the ground, the science return jumps. A minimal human outpost, even with a small crew, can carry and deploy instruments that rival or beat several big robotic missions combined. You can set up seismometers to listen to Mars quakes and probe the interior structure. You can tow ground-penetrating radar systems behind rovers to map subsurface ice and layering. You can run drill rigs that go meters into the ground, pulling out cores that preserve delicate chemical and structural information. You can also run small labs inside the habitat, doing organic chemistry, mineralogy, and imaging on-site, instead of waiting for a sample return. A scientist on Mars can see a rock, decide in seconds if it's interesting, pick it up, analyze it locally, and adjust the plan for the next day. That kind of fast feedback is almost impossible with the long communication delays and slow command cycles of robotic missions. But if you think most of Mars' work is going to look like people planting flags and collecting pretty rocks, you're missing the bulk of the job. A lot of what crews do on the surface will be construction and maintenance. You need landing pads to avoid blasting your own base with dust and rocks every time a ship arrives. You need trenches and buried cables for power and data. You need to assemble towers for communications and weather instruments. You need to deploy and maintain solar fields, reactors, radiators, and ISRU plants. All of that is manual labor in a bulky suit in low gravity at temperatures that can sit around minus 50 degrees Celsius, minus 58 Fahrenheit, or worse. Your hands are in pressurized gloves that make fine manipulation tiring. Your movements are restricted. You get hot inside the suit while the outside is freezing, and your cooling system has to carry that heat away. Simple tasks, turning bolts, dragging hoses, hammering stakes, become slower and more physically demanding. Every hour outside is planned because the risk envelope for an EVA on Mars is narrow. A tear in a glove, even a small one, is an emergency. A stuck valve in your suit's life support, a failing fan, a misbehaving CO2 scrubber, all need fast response. If a rover breaks down 10 kilometers from the base, about 6 miles, that's not a casual walk back in a Mars suit, especially if someone is injured or you're low on consumables. So EVAs are planned more like deep dives in the ocean than like hikes. You define how long you'll be out, how far you'll go, exactly which route you'll take, where the nearest shelter or rover is at every point, how much oxygen, cooling, and power margin you're carrying, and what you'll drop first if things go wrong. You build in abort paths, shorter routes back, and backup ways to get a second rover or crew out if one team gets stuck. Communication delays make this even sharper. On the Moon, ground control can talk to you almost in real time. On Mars, by the time Earth hears you say we have a problem, several minutes may have passed since you said it, and several more minutes will pass before you hear a reply. You don't have time to wait. You and your team have to diagnose and act right there with procedures you trained for and hardware you have. That means checklists, training, and real-time decision-making shift to the crew. Mission control turns into a slower advisory layer, not a joystick. The whole surface ops system, rovers, suits, shelters, procedures, has to be built on the assumption that help from Earth will always be late. And that brings you right up against the next fundamental limit. Even your voice can't outrun the speed of light. Mars is not just far in distance, it's far in time. Every command, every question, every cry for help travels on a 4 to 22-minute delay, one way. So how do you run a mission, coordinate a base, and make critical calls when you can't have a real-time conversation with the planet that built all your hardware? How do you run a mission when even light itself is too slow to save you in an emergency? That's the reality for Mars. Distance doesn't just stretch lines on a map, it stretches time. Every signal, every status update, every "we have a problem" has to cross tens to hundreds of millions of kilometers, and there is no way around the speed of light. Between Earth and Mars, the one-way light time swings from around 4 minutes at close approach to about 22 minutes when they're far apart. That means a simple question and answer can take almost 3/4 of an hour. There is no real-time conversation, no live back and forth. You can't joystick a rover in front of you from Earth. You can't have mission control talking you through a failure second by second. Call home stops meaning talk and turns into send mail with a lag. So if something breaks during an EVA or you see a worrying sensor reading in the habitat, you can't say, "Hold on, let's see what Houston thinks," and wait. By the time they even hear your voice, the situation on Mars has already moved on. That delay changes the whole philosophy of how you train, how you design procedures, and how you split responsibilities between the people on Mars and the people on Earth. On Apollo, mission control could step in almost instantly. They watched telemetry in real time, saw abnormal readings as soon as they happened, and could direct the crew through complex checklists like they did during Apollo 13. On Mars, that model collapses. The crew has to act as their own mission control for anything that unfolds faster than half an hour. Training can't just be memorize this checklist, follow steps 1 through 20 while Houston watches. It has to be understand the systems deeply enough that you can reason about failures yourself. Everyone on the crew needs to be more than a button pusher. Engineers have to think like operators. Operators have to think like designers. If a valve sticks, or a pump starts drawing too much current, or power usage spikes, the first line of analysis is the crew right there, not a room full of specialists on Earth. That doesn't mean Earth is irrelevant. Mission support will still run simulations, analyze long-term trends, and send updated procedures. But their role shifts from real-time control to slow guidance and big-picture optimization. You can think of them as a very smart, very distant back office, not a direct hand on the controls. And even when you're sending normal data, you're limited by bandwidth and coverage. A Mars base will likely talk to Earth mostly through relay satellites around Mars or in heliocentric orbits, not through giant direct-to-Earth antennas all the time. Data rates in early missions might be a few megabits per second when links are good, not the multi-gigabit fiber you're used to at home. Coverage won't necessarily be continuous either. You'll have windows when satellites are in view and times when they're not. That forces hard choices about what you send. Every gigabyte of video, science data, system logs, and personal messages has to be prioritized and scheduled. Raw, high-res video of every EVA? Probably not. You compress, filter, and select. Maybe you send downsampled video and keep the full resolution files locally unless mission control specifically asks for them. You batch telemetry or send detailed logs only when something looks suspicious. Science teams on Earth want data. Engineers want logs. Psychologists want crew health and behavior metrics. Everyone wants more, but the pipe is limited and can't just be upgraded like a ground network. That means some science has to be done and decided locally with summaries sent back instead of streaming every detail to Earth to analyze at leisure. To cope with all that and avoid overloading the crew with constant micromanagement of systems, you lean heavily on automation. AI and autonomous control software start to look less like fancy extras and more like basic tools. Power management systems can automatically balance loads, throttle non-critical equipment, and charge batteries based on forecasts. Thermal control systems can adjust heater and radiator settings without human intervention. ISRU plants can monitor themselves, detect simple faults, and run recoveries without waking up the crew at 0300 hours. But every layer of automation is also another thing that can fail in interesting ways. A software bug in power management could shut down something it shouldn't. A misconfigured algorithm could misinterpret sensor noise as a fault and take a system offline. Or worse, ignore a real fault. You end up needing meta-systems that watch the automation and people who understand enough to step in and override it when behavior looks wrong. So autonomy is not just for robots, it's also for the human systems themselves. The base has to be able to run in a kind of local control mode as the default, with Earth as a slow external advisor rather than master. That applies not just to machines, but to decision-making. Governance sounds abstract, but in Mars it becomes very practical. When you can't get immediate instructions, you need crystal clear rules about who decides what. Who has the authority to scrub a landing because conditions look bad? Who decides to shut down an ISRU plant that's misbehaving, knowing that might impact fuel production for the return trip? Who handles conflicts between science priorities and safety margins? Early crews will likely be a mix of scientists, engineers, and test pilot types, used to taking responsibility and making decisions under pressure. But they'll also have to act as local leadership for the base. That means they need frameworks agreed in advance, laying out which decisions rest entirely on Mars, which decisions require consultation with Earth when time allows, and which decisions are never left to a single person. You also need protocols for disagreement between Mars and Earth. If the crew thinks an EVA is too risky based on what they see on the ground, but Earth thinks the data looks fine, whose judgment wins? If Earth wants to push power systems harder to meet a science goal, and the crew is seeing worrying signs of wear, who has the final say? That needs to be resolved before the mission ever launches, not in the middle of an argument with a 20-minute delay. And remember, this isn't just about safety calls. As the base grows, questions about resources, work schedules, expansion plans, even local culture and rules of conduct start to appear. You're basically establishing the first steps of off-world governance with people who can't be micromanaged from a control room on Earth because the physics won't let you. So by the time you've added up the light speed delay, limited bandwidth, heavy automation, and local decision-making, you're not just visiting Mars anymore. You're running a semi-independent outpost. If that outpost keeps growing, the conversation will eventually shift from how do we keep a small base alive to can we actually reshape this planet to be more like Earth? And that's where the dream of terraforming slams straight into the hardest constraints of physics and planetary science. Why do people talk so casually about terraforming Mars when the numbers say it's basically a planetary-scale construction project far beyond anything humanity has ever done? Turning a cold, thin-air world into something you can walk on without a suit is not turn on a few machines. It's rewrite the entire atmosphere, and the scale is brutal. Start with the basic question. How much air do you actually need for Mars to feel even remotely Earth-like? If you aim for about half of Earth's sea level pressure, around 0.5 bar, that's still plenty to breathe with the right oxygen mix and no pressure suit. To get Mars up to that, you're talking about adding on the order of 10 to the 18 kilograms of gas to the atmosphere. Say that slowly in your head. 10 to the 18 kilograms. That's a billion kilograms. In imperial terms, that's something like 2 billion pounds of gas. No human-built industrial system has ever handled anything close to that. All of our refineries, power plants, and factories combined over their entire lifetimes haven't processed anything on that scale. So when someone says, we'll just make more atmosphere, this is the weight of what that sentence is hiding. You're not tweaking the climate, you're rebuilding it from near zero. So you might ask, fine, but Mars already has carbon dioxide locked up as ice and rock. Can't we just warm the planet, release that CO2, and let the atmosphere thicken itself? This is the classic melt the caps and the soil terraforming idea. The problem is the inventory is smaller than people think. Even if you vaporized all the known CO2 at the poles and released all the CO2 that's loosely bound in near-surface materials, models suggest you'd only get at most a few tens of millibars of extra pressure. That's maybe a few percent of Earth's sea level pressure. It's more than Mars has now, and it might help with greenhouse warming a bit, but it's still far, far below breathable conditions. You'd still need pressure suits outside, you'd still be living in sealed habitats. In other words, Mars doesn't seem to have a secret giant tank of easily accessible CO2 waiting to be released. The total accessible stock just isn't enough to get you to 0.5 bar or 1 bar. You can raise the pressure somewhat, you can warm the surface somewhat, but you don't get to shirt sleeve environment with just local CO2. The physics and the geology push back hard on the simple version of the terraforming story. So the next question is obvious and uncomfortable. If Mars doesn't have enough gas, do you import it? People have suggested redirecting icy asteroids or comets, bodies hundreds of meters across, and smashing them into Mars to add water and volatiles. On paper, that gives you extra mass for atmosphere and maybe more greenhouse gas. But think about the energy involved. A chunk of rock and ice a few hundred meters wide, moving at several kilometers per second, carries an enormous amount of kinetic energy. When it hits, that energy has to go somewhere, mostly into heat and shock. One bad trajectory, one object that's a bit too large or too fast, and instead of a controlled climate boost, you get global firestorms, ejecta, shock waves, and a long, deep impact winter. You're not tuning the planet. You're dropping bombs the size of mountains. Even if you aim smaller with many more modest impacts, you're still running a dangerous experiment with a whole world. Each redirected object needs precise navigation, long-term tracking, and fail-safe systems. The number of successful heavy redirections humanity has done so far is 0. Trying to do this repeatedly, safely for centuries pushes planetary engineering into a risk zone that's very hard to justify when people are already living on the surface. Let's say you ignore those risks and assume you somehow have the right volatiles. There's another hard limit: time. The timescales for global climate and ecosystem changes are not human scale. Even optimistic scenarios that gloss over engineering constraints talk in terms of centuries to millennia to meaningfully thicken the atmosphere, warm the average surface temperature, and establish stable, self-sustaining biospheres. That doesn't match the way we plan missions. Space programs think in decades, corporate timelines think in quarters and years, human lives span maybe 70 to 90 years. Terraforming, in the full sense of the word, requires planning that stretches over many human generations, staying stable through war changes, economic swings, and technological shifts. That's not build a base and expand it. That's run a continuous planetary project longer than any civilization we've ever had. So the realistic picture near term is not turn Mars into a second Earth, it's build islands of habitability. You focus on pressurized bases, buried habitats, maybe interconnected tunnels or domes, and you make the inside as Earth-like as you can. Outside stays hostile. You might make small regional climate tweaks over time, but the main strategy is local control, not global transformation. Then there's a question that often gets pushed aside when people get excited about terraforming. Should we even do it if we could? If Mars has life now, probably microbial and deep underground, or if it once had life and there are relics and biosignatures preserved in the rocks, do we have the right to overwrite that with a new environment built for humans? Planetary protection rules already exist to limit forward contamination, the spread of Earth microbes to other worlds. Because once you seed a planet with our biology, it becomes much harder to study whatever was there originally. For Mars, this matters a lot because it's one of the best candidates to answer the question, did life arise twice, independently, in one solar system? Terraforming at large scale would bury that question under a wave of imported organisms. There's also the ethical side of altering a whole planet for one species' convenience. Terraforming isn't just an engineering problem, it's a moral and scientific one. Do we treat Mars as a place to study and respect, even if it's lifeless now, or as raw material to be reshaped however we want? Do we accept that early human presences will damage some parts of its original state just by existing, but draw a line before global modification? Those questions don't have simple answers. Different cultures, nations, and groups will disagree, but they can't be ignored because once you start large-scale changes, you can't easily roll them back. That's why for the foreseeable future, the smart path looks less like turn Mars into the second Earth and more like learn how to stay alive in controlled pockets using local resources, while we figure out whether Mars is just a new frontier or something we have a responsibility to leave mostly alone. And that brings everything to the real endgame question. If full terraforming is out of reach for now, but outposts are possible, what does an actual roadmap from today's technology to a long-term, stable Mars presence look like step by step? Because you can't jump from zero to city, you have to climb a ladder, and every rung on that ladder is a full program on its own. The first step is not Mars at all, it's near Earth. Before you bet human lives on a 3-year mission, you prove the tech where you can still bring people home in a few days. That means long-duration habitats in lunar orbit and on the moon's surface. You test closed-loop life support there not for 6 months, but for years, with crews rotating in and out. You push water recycling, oxygen recovery, and waste handling until you see what really breaks after thousands of hours. You also test partial gravity the only way we can in the near term, by actually living in less than 1 g. The moon gives you about 1/6 of Earth's gravity, which is not Mars, but it's better than zero. You see how bones, muscles, and hearts react over long stays, and whether your exercise and medical protocols hold up. On top of that, you test nuclear power systems safely near home, and you try out ISRU in a forgiving environment, pulling oxygen out of lunar regolith, extracting water ice from polar craters, and learning how dust and temperature swings chew up your equipment. The key idea is simple. You fix the stupid failures while home is still a 3-day burn away, not months. Once you can keep a small crew running in hostile places near Earth without constant resupply, you move to step 2, robotic cargo campaigns to Mars. Before a single person straps in for the ride, you send hardware, lots of it. Landers carry uncrewed habitats, power units, maybe compact reactors or huge solar fields and their cleaning systems, plus ISRU plants and piles of supplies. These missions need to prove more than we landed. They need to show continuous fuel production, not grams per hour in a lab, but tons per year from Martian air and ice. You want tanks on the ground slowly filling with methane and oxygen for a future ascent vehicle. You also send drilling packages and detailed surveying gear to map local ice, rock types, and dust properties around your intended base site. Over several launch windows, every 26 months or so, you build up a cluster of assets on Mars that talk to each other, share power, and run mostly on their own, while engineers on Earth monitor performance and refine designs. By the time you're done, the base site isn't empty. It's a robot-run industrial yard waiting for humans. Only after that do you take step 3, sending the first crews. And even then, you don't lock them in for 500 days on the surface. Initial human missions are short stays, 30 to 90 days on Mars, before they get back on the earliest easy return option. Think of these as shakedown cruises for the base. The crew lands near pre-deployed habitats, inspects them, moves in, and lives there for a few weeks or months under real conditions, with real risk, but a relatively quick path home. During that time, they validate that the ISRU plants are actually producing fuel and oxygen at the promised rates, not just blinking green lights. They run emergency drills, simulating fires, leaks, suit failures, and medical events. They test every backup system. They deliberately stress the power grid. They make sure landing pads don't sandblast nearby hardware, and they push the rovers and suits through hard fieldwork. A big part of their job is not heroic exploration, it's trying to break things in controlled ways, then writing down what failed and why. When they leave, the base should be in better shape than when they arrived, with more data, more confidence, and more realistic procedures. If those early missions work and nothing fundamental turns out to be a showstopper, you move to step 4. Long-stay missions and real expansion. Now, crews commit to full 500-day surface cycles, staying on Mars from one good return window to the next. That means living through seasons, dust storms, and at least one full Martian winter with all the power and heating challenges that brings. Habitat area grows from a couple of modules to a distributed base with hundreds, then thousands of square meters of usable floor space, roughly tens of thousands of square feet. You add dedicated greenhouses that provide a fraction of the food and help close the water and oxygen loops. You add more power units, more ISRU capacity, more storage, more workshops. The crew count bumps from a handful of pioneers, maybe 4 to 6, up to a dozen, then a few dozen, rotating in overlapping shifts so knowledge doesn't reset to zero each time. With more people and more equipment, you can start doing heavier construction, like covered tunnels, partly buried domes, or regolith shielded vaults. You can afford to dedicate some crew time to pure science while others maintain infrastructure instead of everyone doing everything. You can experiment with small-scale manufacturing using 3D printers and local materials to make replacement parts, structural elements, and simple tools. The base shifts from camp that constantly worries about survival toward outposts that can handle some surprises. Only after multiple long-stay cycles, and only if the base has proven it can handle equipment failures, medical events, power dips, and crew turnover without skating on the edge of disaster every time, do you even start talking seriously about Step 5, going from outpost to city. And here, city is not a catchy label, it means specific things. A true Mars city would mean thousands of residents, not dozens. It would mean local manufacturing of bulk structural materials like metals, ceramics, glass, and composites in quantities large enough to build new habitats, towers, tunnels, and vehicles without shipping every beam and panel from Earth. It might mean limited chip fabrication or electronics assembly lines on Mars, so the base isn't crippled when one mission's worth of electronics spares runs out. It could mean small pharmaceutical production capability instead of depending entirely on periodic resupply. You'd see a regular transport cadence emerge, ships arriving and departing every 26 months, filling and emptying orbital depots and surface tanks. Some flights would be moving people, others heavy cargo, others raw materials and specialized equipment. There would be local governance on Mars, because at that scale, you're not just running a mission, you're running a community with its own rules, norms, and internal economy, still tightly linked to Earth but not micromanaged by it. The timeline for that is not this decade, and probably not the next either. It's a multi-generational project. The first kids raised partly in Mars gravity would grow up under different medical and social conditions than any humans before them. Engineering standards, building codes, environmental rules, and even cultural attitudes toward risk would evolve differently on Mars than on Earth. It stops being a mission and starts being a civilization branch. So when you hear "we're going to Mars," the real meaning, if you follow it all the way out, is not "we'll plant a flag and come home." It's "we're committing to a chain of steps that starts with test habitats in lunar orbit, runs through robotic fuel plants on a cold red desert, and ends, maybe centuries from now, with a permanent off-world society that either thrives under alien skies or proves the hard way that leaving Earth is even more difficult than the most pessimistic engineers said out loud. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.